concrete recycling gets a high-value upgrade. Concrete is getting a second look, not as waste, but as a resource with unrealized potential. As construction faces mounting pressure to cut emissions, attention is shifting to how materials are treated at end of life. Instead of defaulting to downcycling, researchers and engineers are exploring ways to recover value from what was previously discarded. The implications go beyond sustainability targets. If these approaches scale, they could reshape cost structures, supply chains, and how the industry defines material efficiency. Rethinking concrete waste streams. Traditional recycling methods have focused on crushing demolished concrete into aggregates for reuse in lower grade applications. While this reduces landfill volumes, it overlooks a significant portion of the material, fine particles produced during processing. These fines, often making up a substantial share of recycled output, have typically been sidelined due to their porosity and weak structural performance. However, recent research indicates they contain a high proportion of residual cement content, making them a viable candidate for reactivation. This shift in perspective matters. Cement production remains one of the largest industrial sources of carbon emissions. Recovering usable material from existing concrete could reduce demand for virgin inputs while easing cost and supply pressures tied to raw materials. Restoring reactivity through material engineering. Emerging technologies are challenging the assumption that hardened concrete is chemically inactive. Instead, they treat it as a material with dormant reactivity that can be reawakened through targeted processes. One method uses high-energy mechanical treatment to alter the internal structure of recycled concrete fines. Through intense particle collisions, defects are introduced into the material's crystal lattice, restoring its ability to participate in chemical reactions. This allows the material to function as a supplementary cementitious component in new mixes. Another approach enhances particle performance through surface modification. By bonding reactive materials such as slag or silica fume onto recycled particles, engineers can create composite materials with improved strength and durability characteristics. The result is not just recycled input, but a designed material with predictable performance. These developments move concrete recycling beyond basic reuse into a more advanced phase of material engineering, where properties can be tuned at the microscopic level. Expanding beyond concrete, the same techniques are being applied to other industrial byproducts, including steel slag and excavation waste. This signals a broader shift toward integrating circular principles into construction materials at scale. For industry stakeholders, the appeal lies in compatibility with existing infrastructure. Early indications suggest these processes can be implemented using current industrial equipment, reducing barriers to adoption. At the same time, the potential applications are expanding. Reengineered materials could support new forms of concrete with enhanced durability or specialized functions, aligning with growing demand for smarter and more resilient infrastructure. What's emerging is less about improving recycling rates and more about redefining waste itself, positioning it as a feedstock for the next generation of construction materials.